Okay, welcome, guys. So this thing is indeed the unit circle. Or is it? We're going to talk about that. So, first off, you'll notice the homework is very short. That's because we're going to waste a lot of time talking about this, and we're not going to get too far into polar coordinates quite yet. So, let's talk about this, though. So, let me make sure I'm recording. Yes, I'm recording. Okay. So, alright. What I suggested that you do is solve each of these for t, both of them, for t, and then set them equal to each other. Now, Victor, I saw what you did. You solved this one for t and then plugged that in for t, and then you just stopped and said, I'm done. But I told you, you know what object this is. Though technically you did get a expression in y and x, so that's technically okay. But the idea was, like, you should be able to name what object this is. You've seen it before, I said. And so when you do that, right, so it looks like both of you guys got this, but I just want to talk about this briefly. You rearrange this, right? You bring the 1 up and you get x plus xt squared, and now you're quadratic in t, and what you end up getting is that t is plus or minus the square root of, I wrote it as 1 minus x over 1 plus x. You do the same thing here, and I want to actually write this one out. You get y t squared plus y equals 2t, but then you bring the 2t over and you get the minus 2t right there equals 0.
And then you have to use the quadratic.
Then you use the quadratic, and I reduced it to get that y is equal to y plus or minus the square root of 1 minus y squared over y. Yeah?
Oh.
That's, or y, t. Yeah. It was like 2 plus or minus 4 minus 4 y squared. You can pull the 4 out as a 2. Cancel that 2 down with the 2 that's in the denominator. It makes your life a little easier. It doesn't make it that much easier because it's still a lot of stuff to do. But then you set these two things equal to each other and you say, well, I have a square root, so let me square both sides. And I'm not going to write out this whole thing, right? In fact, here, I'll do this if you're really interested. This will be on YouTube, and you could pause this at any point. This is how I did it. You could like pause this and see just what a terrible mess this is. And okay, so pause that and figure that out. So, but there are just a few things I want to go over here with this. But anyways, you set that equal to that. Square both sides. This gets really ugly. On one side, you end up with that, and
I squared both sides then.
What now?
I squared both sides. I don't remember what I did.
Well, you should, if you have something like this, equals 1 plus or minus or root and blah, 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 blah. Got to get rid of that guy. So you square both sides. This thing gets kind of ugly. But now you have 1 minus x over 1 plus x. Bring the y squared upstairs. Y squared. This thing ends up being really ugly, but it gives you, I'll just write it, you get 1 plus or minus 2 root 1 minus y squared plus 1 minus y squared. You bring all this stuff over to that side. And the way I did it, I put it all over a common denominator. You don't have to, but it makes your life easier if you do, because I'm going to write it up here to give myself some room. But like I said, if you're really interested, you can see this. You end up getting a y squared minus xy squared minus 2 minus 2x plus y squared plus xy squared all over 1 plus x is equal to plus or minus 2 root 1 minus y squared. Nice thing is this and that cancel. This ends up being a 2y squared minus 2 minus 2x over some stuff. This is a plus or minus 2 something. And so those cancel out nice. And it turns into something actually not that bad. What you end up getting is y squared minus x minus 1 over 1 plus x equals plus or minus root 1 minus y squared. Why did I do that in the first place? Well, I noticed after I squared that thing, I still had a root over here, so I know that I need to get everything else over there and then do the same kind of trick to get that root gone. Square that guy. This gets a little ugly. It gets, well, okay, it gets very ugly. And
square a quadratic.
Yeah. So you're squaring a trinomial
Yeah.
here, and so it gets really ugly. It comes out to be like 1 plus 2x plus x squared at the bottom. This ends up being y to the 4th plus 2xy squared minus 2y squared plus x squared plus 2x plus 1 equals 1 minus y squared. Really, really ugly. Bring this guy upstairs, right? So now you're taking this thing multiplied by that thing, and then a bunch of stuff cancels out. So I'm, in between each of these, I'm skipping a bunch of steps. But once you do that, once you bring him up here, multiply that out, pretty much all of this cancels out. Then there's some terms that you bring over, and what you end up getting, here we go, is y to the 4th minus y squared plus x squared y squared equals 0. Is there something common you could factor out of there? Or just divide everybody through by y squared. When you divide everybody through by y squared, you get y squared minus 1 plus x squared equals 0, which is, oh, lo and behold, I know what this is. This is x squared plus y squared equals 1. That's the unit circle!
Yeah, I got that in a very different way.
Or is it the unit circle? And so this is what we're going to kind of talk about this, because this is interesting. And one thing we're going to talk about while analyzing this will be like part of the bread and butter of the first part of calculus.
There's certain steps where it wouldn't have been, because you divide by.
This is what we're going to talk about. So watch this. So first thing you notice is when we took this step, we're implicitly assuming that y cannot equal 0, right? Because you divided by y squared, right? So you're implicitly assuming y doesn't equal 0. But what if y were 0? Well, hold up. If y is 0, you wouldn't have done this in the first place, would you? Right? Like if y were 0, this equation would reduce down to 2t equals 0, which means that t equals what?
0.
0, right? Or even from the very beginning, if you'd started with this right here, and you're going to go solve for t, you'd say, well, okay, if 0 is equal to 2t, oh yeah, t equals 0. Is that legit? Is t in the domain of this thing? Is 0 in the domain? Yeah. When I plug it in, do I have any problems here? No. When I plug it in, do I have any problems here? No, it's perfectly good. In fact, when I plug in a t equals 0, I get y equals 0, x equals 1, so that gives me actually one of my parts. So it turns out that y equals 0 thing, you don't really need to worry about it. You could kind of nitpick about it and say, well, but even here, look, if y is 0, is that still a true equation? Yeah, it's still going to give you 0. So it's one of those, you don't really need to worry about that too much. But, okay, let's see. So, okay. There's another problem. With what? Hey, buddy. With what?
This square root. No, because they're all plus or minus. Wait, I don't know.
There's a problem. So we talked about this guy here.
Yeah.
What about this guy? What's a problem? What might be a problem in that right there?
It can't be negative. But then the plus or minus sort of takes care of that.
There's another problem.
Oh, x can equal negative.
Aha! If x is equal to -1, then that blows up, doesn't it? So it's starting to look like that x cannot equal -1. Now you could try to verify this by saying, well, what happens if x is... Let's suppose that it's possible that x equals -1. Then what happens? Well, 1 minus t squared. We're asking ourselves now, when does that occur? For what time do you get x equal to -1? And then so I'm going to bring him upstairs. -1 times this gives me a -1 minus t squared. Yeah, everybody saw what I did there, right? Just brought him upstairs, multiply by a negative. Okay.
And you get
Now let's add t squared to both sides, and that gives me negative 1 is equal to 1, which gives me that 0 is equal to 2, which means that 0 is equal to 1. Uh-oh. That's bad. That's never true. That's really, really bad. That can't happen. So I'm starting to think that x can never be negative 1.
But it can for...
Or can it? And so this is the thing. So we will talk about this in calculus a lot, but check this out. Let's just graph x. And if you were to graph x, now I'm talking about this function, x of t. X as a function of t, which is the function 1 minus t squared over 1 plus t squared. The input axis is t. And what this thing looks like, something like this. So here at 1, right, when I plug in a 0, I get out a 1.
Yeah.
Right, and then it does something like this. It does something like that. And it turns out, this is an asymptote right here.
At -1.
It's an asymptote. So in other words, the bigger that t gets, this function gets closer and closer and closer to -1. And another thing it means, like what an asymptote is that this tells you that you could get as close to -1 as you want. If you want to get within 1 trillionth of -1, in other words, you want to be at most, like, here I'm going to write down 20 zeros and then a 1. If you want to be that close, you can find it. You just keep going in t, and eventually you'll get that close. You want to get twice as close as that, like you want to get another 0.0. You want to get that close to -1, just keep going that way. Or that way, and this function will get as close as you want when t is very, very large. And here by large, I mean both in the positive direction and the negative direction. So I'm kind of saying when the absolute value of t is very, very, very large. Okay? Now, let's suppose that t is very, very, very large. Okay, so in other words, if t is very, 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 very large, then we're talking about times when t is not equal to 0. Okay? If t is not equal to 0, watch what we could do. If t is not equal to 0, I could divide by t, right? In fact, I could divide by t squared if I were so inclined. This is a trick we're going to talk about in calculus, where you find the highest order power of your variable. In this case, it's t squared. And we're just going to go divide both the top and the bottom by it. And now, if t is not 0, this is perfectly legit. And if t is not 0, then my original equation is exactly equal to this thing right here, right? I'm just going to distribute him over, and so we get 1 over t squared. Here, minus, well, 1. I do the same thing here. Distribute him over, I get 1 over t squared plus 1. Now, when t is very, 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 very large, then t squared is very, 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 very larger. And so 1 over t squared is like a very, 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 very big number.
No, it's smaller.
But 1 over a very, 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 very big number, it's almost 0. In fact, it's as close as you want to 0. If you want to be within like a trillionth, you can find it. Just take t large enough that it gets you close enough. And so then we say in the limit, as t gets very, very large, this thing goes to 0 minus 1 over 0 plus 1. Everybody see that? Right? We're talking about times where t is not equal to 0 and t is very, very, very big, or very, very, very small. Then we could rewrite x to be this, and it's exactly equal. And it turns out that when you make t very, very, very big, then you get -1. And we have a way of writing this. We'll talk about this in depth in calculus, but the way of writing this is to say that the limit as t goes to infinity of this stuff, 1 minus 2, which is our x function, is equal to -1. That's what that means. That this little statement right here means that if you make t big enough, then you could get the value of this function to be as close to this number as you could possibly want. And in that sense, you could say, then, yeah, x could be -1. In the limit, you know, whatever that means. Okay, so yeah, we're gonna do this in calculus. But I do wanna, I also, before we finish up, I want to apply the same logic and show you that the same thing that we just did here, the same trick, it does apply to y as well. And so, kind of following suit from what we did before, I want to look at, I want to graph y. This is y, we're going to think about it as a function of t. Y of t is 2t over 1 plus t squared, and if we graph it, t is my input, y is my output. It looks like this. Pops up, and it comes down, and it approaches that. Yeah, drops it, points down, and turns out that these guys, you never need to worry about imaginary numbers popping out because of this type of thing. Like, it never gets negative.
Yeah.
You know, I mean, you could plug in just a big X, but you don't because of this. Like, this is why this never gets bigger than 1. This never gets bigger than -1. So it does that. But again, we have an asymptote. It turns out that y equals 0 is your asymptote as you go this way and that way. And so let's do the same kind of analysis. Let's see what would happen. I could say, I remember how I did this. I said, okay, I want to find out what happens when t is very, 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 very big. And so when t is very, very, very big, t is not equal to 0, so it makes perfect sense to divide by whatever. And the thing I'm going to do, I'm going to look here and find the highest power, the highest order term, is t squared. So I'm going to do that. I'm going to divide by whatever that is on the top and the bottom. So 1 over t squared. 1 over t squared. And as long as t is not equal to 0, which is what we're talking about, then this is perfectly valid. And the thing that I get, which is 2 over t on the top, and then 1 over t squared plus 1 on the bottom. These are exactly equal as long as t is not equal to 0. And we're so far away from 0 that it won't matter. But now what happens? Well,
that's basically 0.
This goes to basically 0. And what does that go to when t gets very, 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 very big?
0.
So 0, right? And that's kind of the cool thing about this. It's like, oh, yeah. And so then that's the same thing as 0 over 1, which is what?
0.
So we would say that this function, that the limit of this function, 2t over 1 plus t squared, as t goes to infinity, or negative infinity, because of the square, I mean, like, okay, it's negative, but it's still going to 0. This still happens, but it's neither here nor there, is 0. And so, let's think about what we just said. When t goes to either positive or negative infinity, then we know that this goes to -1. And when t goes to positive or negative infinity, we know that this goes to 0. Well, that's a point on the unit circle, isn't it? And it turns out that if you were to just parameterize this guy, plug in a t equals 0, and now we're graphing x and y here. When t equals 0, we saw x equals 1, y equals 0, so you're at this point. And then as t gets bigger, when t equals 1, you're right here. Let's just check that. Plug in a 1, you get 1 minus 1 is 0. Not going to bother with the denominator. X is equal to 0, so x is right there. Plug in a 1 right here, you get a 2 over 1 plus 1, 2 over 2 is 1. So you're right here at x equals 0, y equals 1. And then it starts to really slow down. And like, you get like, t is like a couple thousand here, and then t is like 1,000,000, and so on and so forth, and it gets closer and closer and closer and closer to that as you increase t. If you go in the opposite direction, you plug in a t equals -1, you plug in a t equals 100 or 1,000 or whatever, and you keep going and eventually it goes there. And then we could say, well, this isn't quite the unit circle because you're missing that point because you're not actually getting to infinity, but you could just say that in the limit, then you do get that point. And they both go to the same place, whether, regardless of how you're going. But so, is it really the unit circle? Yeah, kind of. Is it really this? Yeah. If we do some kind of magic and say in the limit, whatever that means, like if you
also just proved it is the unit circle.
Well,
but no, we just assumed it.
Did we? I mean, because again, it's like, there are, because there are a couple problems. We divided by y, which could be 0. And back up here, we said, well, yeah, this assumes that x is not equal to -1. So, yeah, these types of questions could be answered. And, another thing is these are continuous functions. And if you remember something I said about that, this thing is an open interval. And so this needs to be open as well. So if you think about what you've just done, you've just taken this is like taking the interval -infinity up to infinity and just wrapping it around like this. If you close it up, well, what have you just done? Have you included infinity? And that's way advanced stuff to talk about. We're not going to worry about that. Technically, yeah, we're just going to say, yeah, it's the unit circle. But there's just more going on here. It's not such an easy. It's not so cut and dry. This is one thing I love about math. Like my mom likes to chide me and say, you like math because it's black and white, but it's not at all black and white. There's, it's like, what, is this the unit circle? Well, yes and no, kind of, depending on how you look at it. And I think that's cool, you could make an argument 2 different ways about this. That, yeah, it's kind of like the unit circle, but not quite. But if you want to kind of do, talk about limits and what happens at infinity, then yeah, it's the unit circle. It's perfectly good to talk about. So I think that stuff's cool. Okay. Any questions about anything we've talked about up until now? Because we're moving to a new section, polar coordinates. Are we ready to do this? Okay. I've already talked about this a bunch of times. Even last year, I talked about how you could, if given any point on the plane, let's call it xy, you have some point, doesn't matter where it is on the plane, but we're going to call it the point xy. There's 2 ways we could get there. I could tell you to go x units away from the y-axis and y units away from the x-axis to get there. Or, now that we know some trig, I could say, we all know where 0 is. We call this a pole, by the way, but the 0 is the pole. That's why we're calling it polar coordinates. And we're gonna define an axis. This is the polar axis. And what we're gonna do is say, as long as we're all agreed where that thing is and where this direction is, then what we're gonna do is measure the angle from there to there and the distance. So I could tell you, go theta degrees away from due east and then walk a distance of r. And what we would have is another way of describing the exact same point. And we're going to do it in this order, r, comma, theta. Where theta will be measured in radians, measured from the positive x-axis. Okay? So this is, I've probably said this, what, like 5 times now? Everybody expected this. I'm not saying anything new here. Okay? Alright. Yeah, I want to do this example first. So let's do this example. So, I'm just going to jump right into it. Find the polar form That is, I'm looking for an r and a theta. Find the polar form of the point negative root 3 comma 1. And in everything you're going to do in this homework, and probably all the other, no, I'm sorry, but at least for this homework, I want to say the first thing you want to do is guess what? Guess what I want you to do first before you do anything else with this.
Draw a triangle. Graph it.
Graph it. And we will be using triangles, yes, but the first thing you do is graph it. And so negative root 3 is over here. There's negative root 3. Here's the point 1. So there's the point that I'm given. Now what we're asking is you give me directions to get to that point only by doing it this way, where you're measuring from here to here. Oh, shivada. Okay. So what did you just say?
2 negative pi over 6 would be
2
Oh.
negative?
Or
Wait
you
a
just-
second. Wait a second. So first off,
uh,
is this a triangle that you recognize?
yes.
Yes.
Yeah, and all of them will be.
Oh.
All of them will be. Well, except, okay, we're going to do an example where it's not. But almost all of these are going to be a triangle you recognize. What? So, I'm going to put my pen up here. You tell me what to write. What do I write here?
1.
What do I write here?
Root 3.
What do I write here?
2.
What do I write here?
Pi over 6.
Yeah.
It'd be pi over 6 plus pi over 2. Right? For that.
Wait a second. Wait.
Yeah.
Just wait. So, what does that mean that r is now?
2.
The r is 2. So we're halfway there, right? We're looking for r comma theta. R is a 2. Now, theta, mind you, is measured from here to here. And so we know that this is what?
Pi over 6.
Pi over 6, which means
Wait,
that
wait.
theta is what?
Oh, pi over 6 minus pi.
Looks like a...
Yeah, pi minus pi over
minus
6.
pi.
Pi minus pi over 6, which is what?
Pi over 6.
Now what's really going to help you out is instead of thinking about this as like, wait, pi minus this and this and that, if you just remember this thing that I told you to memorize from like day 1, right? Like if you know where all of the spokes on the, what we call them the principal angles, if you know where all of those spokes are, like if I say, oh yeah, the one that comes down here where that's pi over 3, that's the, let's see, if that's 3 pi over 3, then that must be 4 pi over 3. Then your life is going to be so much easier than if you're trying to do this without that knowledge. Because now everything that you should have memorized with this, it's going to come into play. Okay, so this is, yeah, so this is that. And like conversely, I could have said, hey, here's a point on the plane. And we understand that this is in polar coordinates, so you know that that's 2 units away from the origin. In that direction, you could have said, okay, 5 pi over 6 is, because I memorized that thing that Justin told me to memorize, I know that 5 pi over 6 is right there. Meaning, like, that's 5 pi over 6, meaning that that's pi over 6. And I know if my unit, oh wait, if that's pi over 6, I know a triangle, right? And you can say, if I know that that's 2, hey, that's one of those triangles that I know. And so then my x coordinate would be negative root 3. And my y coordinate would be positive 1. Lo and behold, they're the same point. Okay? Everybody get that? If you do it graphically and use the known triangles and the principal angles, your life is going to be so easy. If you try to be creative or just make it way harder, like you kept saying like negative pi. Like,
Yeah.
wait, no, you're thinking too hard. But I mean, you're right. Like negative pi over 6 plus pi, or what, however you want to think about it. But just think about how you could draw a triangle. But now this is a very beautiful, and I mean that seriously, like the things you could do with polar coordinates, and like it's really cool. But there's a problem. Is that the points on the plane are not unique. So this is the one we just had, right? 5 pi over 6. And it's 2 units away, okay? So we called this point 2 5 pi over 6, which was, by the way, remember, the same thing as negative root 3, 1. We're going to call these rectangular or Cartesian coordinates. Those are the old school coordinates that we know and love, right? In Cartesian coordinates, this point was negative root 3, 1. In polar coordinates, it was 2 and 5 pi over 6, but these are not unique. You could have, if you were so inclined, said, well, you know, if you go from here to here, that would be, if you're moving in the opposite direction, that would be negative 7 pi over 6, right? Because that would be 6 pi over 6. 1 more pi over 6 would be negative 7 pi over 6. So you could have said, well, that's 2 negative 7 pi over 6.
It's the same thing.
It's the same thing. Or we could have said, well, hold up.
Just add 2 pi.
Yeah, exactly. You could have said, well, you could get there by just wrapping around once. So now you're at 2 pi and another 5 pi over 6 for a total of 217 pi over 6. 17, yeah, 17. Now this is where it's really going to break your brain. Watch what happens when I do this. What if I go down negative pi over 6 and then go in the negative direction? So you get negative 2. Yes, your radius can be negative. Ooh. So that's tricky. But these are all the same point.
Yeah.
Now another thing I could have done, I could have gotten to that same place by saying 11 pi over 6. So I could go, okay, 11 pi over 6. 11 pi over 6. But again, now that you're here, you've gone 11 pi over 6, now go negative 2 that way. Ah, yeah. And so this is tricky, right? That this is one of the downfalls, or not a downfall because it's very useful, but it could be very confusing, right? And you might just look at this point and that point and go, those are not the same point, but they are. They are the same point. Okay? So be careful with that. Your first question? Yeah, it's only one question, but so the first question is on this. Like, are these the same point? Which of these is the same thing as that? Or whatever, right? So, yeah. Okay. So there's that. Questions on this? Drawing this stuff out will be a huge help. As you can imagine, if I just told you, is this the same as that? I have no clue, right? But if you draw it out and go, well, hold up, 5 pi over 6 is there, and then you go out 2. The 11 pi over 6 is down here, and then I go, back 2. Yeah, those are the same ones, but, Okay,
I did a good job.
so that's one of the things you're going to do. Okay, we got time. We're good. So, questions? I'm just going to blow through this stuff. Okay, here's 4b. Now, let's go in the opposite direction. We're going to change coordinates from polar to rectangular. Okay? We're going to change from polar to rectangular, and here is the polar coordinates. Minus 6, 7 pi over 3.
Are these all, okay, 7 pi over 3.
So guess what the first step's going to be? Draw it out. Okay, so first off, and like, I'm going to go find where 7 pi over 3 lives. Where's 7 pi over 3?
It's past.
It's the one.
It's past 2 pi.
Yeah, it is, because 2 pi is
So it's just
6 pi
it's
over
just
3.
pi over
So it's the same as pi over 3. So let's just do that. So there's pi over 3. which is, I'm just going to put it up here. There's 7 pi over 3.
You can use the 36.
And now we're doing minus 6. So where does this guy end up?
Across in the third quadrant.
There you go. Thank you. That's what I was looking for. Third quadrant. So the same bit right there. Third quadrant, which means that this is pi over 3 right there. Now, again, like we've mentioned this before, like this over 3, right? If anything's over 3, if you have radian measures and they're over 3, you're either here, 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 or here. There's only 4 of them. Or, yeah, it could be here. Or it could be, yeah, I guess. And if it's, yeah, but that's not the point, right? Like, then if it's 6, if it's over 6, then you know you're one of these guys down here, right? If it's over 4, it's somewhere in between, right? So this is, again, where this picture is going to make your life much, much easier. So I know that that's basically what it looks like. The reference angle, the angle from the thing to the x-axis is going to be pi over 3.
-1, negative.
So, well, hold up. So I want to talk about it. And so now, and another thing I'm going to do, I'm just going to go ahead and write, like, so that should be 6 units long, right there. Now, there's 2 ways we could do this.
Well, we know the triangle, so we can
Right? And I think scaling the triangle is going to be
We have
much
to
easier.
scale by 3.
There you go. Because, yeah, let's look at that, right? You would have this triangle here. And I'm going to go ahead and write, this is my pi over 3. It would be 1, 2, square root 3 like that. And I'm thinking, what do I need to multiply this guy by in order to turn him into a 6? What do I need to do?
Multiply by 3.
could be
Right, just multiply everybody through by 3.
-3.
And I get 6 here. I get 3, and I get 3 root 3. And so what are my coordinates, my final coordinates?
-3,
Negative 3. Negative 3 root 3. And these are unique.
Wait, wouldn't it? Oh yeah.
Right? Yeah, so double check me, right? So we're in this quadrant, this is that point, and so we've taken the length 3, but it's a -3 because he's over there. Same thing down here. And so we have -3 root 3. Now here's another thing you could do. If you wanted. Like, so scaling the triangle is very easy. But
Could just
another thing you could do is say, well, hold up, wait a second. Yeah, because you could say, well, wait a second, this is just some x value here. This, like this length is just an x value. This length is just a y value. And so I could just say, well then, and remember again, this is not taking into consideration the actual sign, S-I-G-N, of the thing, whether it's positive or negative. But I could say, if that's my x value, that's my y value. If this is 6, then I could just say sine of pi over 3 is equal to opposite over hypotenuse, so y over 6, meaning that 6 sine pi over 3 is y. Sine pi over 3.
3 over 2. Oh, 1. Yeah.
Root 3 over 2.
Oh.
Sine, yeah, I know. I was actually thinking the same thing. Root 3 over 2. 3 root 3 equals y. But we know it's negative, so we get that guy. The exact opposite for cosine of pi over 3. Cosine of pi over 3 is adjacent over hypotenuse, which is x over 6. Bring that guy upstairs. Cosine pi over 3 is adjacent, so that's 1/2. 6 1/2 equals x. So that x is equal to 3. But we know that he's down here, so then we say, okay, it has to be -3. Good to go. Either way you want to do that, it's the same thing, and it's like you might be at this point saying, just shut up. Like, this was way harder than that. Yeah, but that gives us,
This is how you would do it if it wasn't exact. Like if you didn't.
Right.
If you didn't have a triangle.
Right. If you didn't have a triangle that you knew, this is how you would do it, right? And well, what's more is you really don't have to use your brain if you could say, wait a second. If I measure all the way from here to here, right? In other words, well, you could call it, or no, oh no, you couldn't call it 7 pi over 3 in this case because it's in the opposite. You could say, okay, that means that this is pi, what is this? 3 pi over 3. So this would be 4 pi over 3. And then you're just kind of thinking, well, wait a second. If this were a circle, if it were the unit circle, and you were down here at 4 pi over 3, then my point would be at cosine 4 pi over 3 sine 4 pi over 3. That's if it's the unit circle. That's how we define the unit circle. That's how, that's how we define cosine and sine, really. Remember? Like, we started off with the triangles, but then we said it's wherever it is on the unit circle. But then, as we've seen now a bunch of times, if you take that and stretch it to be 6, you got that. Well, the problem with that is now, okay, well, yeah, and so you say, well, then the x-coordinate is just 6 cosine 4 pi over 3. But since that's one that you can calculate, you have to calculate it. And you say, yeah, what's 4 pi over 3? And so then you have to go through this, and you go, well, this is pi over 3. And if that's pi over 3, and this is 2 over 1 over root 3, and so cosine of it would be adjacent over hypotenuse, so that's 1/2. And look, you did the same thing that you would have done the other way, right? So it's kind of like, now, but this is going to be super useful for us because now we could do this in general. And this will be useful for what we're going to be doing later in this same section when we say, well, you'll see. You'll see what we're doing. But this is nice because now we could say, okay, in general, you give me any polar coordinate, and without loss of generality, I'm just going to draw it right here. I could have drawn it over there. I could have drawn it down here. I could have drawn it down here. Whatever. But we're going to say there's theta, that's r. And then what we could do is say, well, then, if you want the x and the y value, then this thing is just x right there from there to there. That thing's a y just from there to there. And you say, well then, cosine theta is equal to x over r, so that r cosine theta is equal to x, I should say. So going from Cartesian to polar, or no, sorry. This is the polar coordinate is r comma theta. The Cartesian coordinate, x comma y, is given by r cosine theta and then sine theta gives us y over r, so that r sine theta is equal to y. Right there. So that's going to be really nice. Yeah, that's a formula, but you have to stop because when r is negative, we just saw that's not going to work so easily. You can't just say, oh, if I want to convert it, I just plug it into here. Okay? Yeah. So that works if theta is, well, you want to try to keep your theta between 0 and 2 pi, just almost always. But there are tricky things that are going to show up in your book that, yeah, but at any rate, this is going to be really, really, really useful, okay? We could just say x is just equal to r cosine theta. Y is equal to r sine theta. That's going to be very useful. Okay, so now here's this. We're going to do one more time. We're going to convert polar to rectangular. But now, so we want polar to rectangular, and now here's the polar coordinate. 10 arc cos negative 1/3. Okay, so what you got to do, first thing, we're going to graph this. You're going to figure out where it is, but here's a question. Arc cos of a negative number.
It's a negative. Oh. Wait, no. No,
You
it's
think
a
of arc
plus.
sine. If this is arc cos,
Oh, yeah.
arc cos x, here's my 1, here's my negative 1, this should be pi over 2, this should be pi.
Between the...
Yeah, so it's going to be between pi over 2 and pi. So, whatever point this is, should be over here somewhere. Okay? So, we already know that its length is 10. So, that's nice. But one thing we could do is say, well, wait a second. Cosine. So, this is the arc cosine. Cosine is what over what?
Adjacent over hypotenuse.
Adjacent over hypotenuse. Or you could say that cosine, we know, is the radius, the x value over the radius, right? Right? Which is, that's how we're going to think about this. Adjacent, yes, is this side when you're measuring your angle from here, right? Or you could just think about it as your x value over your radius. And if that's the case, then your x value would be here at -1. And your radius would be 3, like that. And now we just need to say, well, I need to stretch that thing, right? To have a, what is it? What's that called? Hypotenuse of 10. Right? Or to have a radius of 10. Right? That's what you could do. Because this is the angle. This is theta right there. Theta is equal to arc cos minus 1/3. So it's some number like over here, right? It's some output, theta, that's between pi over 2 and pi. And so there's your theta right there. And if it does that, now we just need to manipulate it so that we get a 10 right there. So, wait, yes, if we multiply them each by 10/3. Multiply by 10/3, multiply by 10/3. Then we end up with a radius of 10. This is down here at -10/3. And now we just need to find out what the height is because we have our x-coordinate, right? Going to rectangular, we have negative. I would use a Pythagorean theorem. That'd be way easy. And just make sure you remember that it's positive because if it were down here, it would be a different matter, right?
Yeah.
So yeah, how about that squared? Well, we'll do it this way. This is my y that I'm looking for, so 10/3 squared plus y squared is equal to 10 squared.
So 10/3 squared is 100 over 9.
100 over 9 minus 100.
Or even 100.
Or how about 100 minus 100 over 9? Careful with that.
And square root.
Yeah.
So that's 900 over 9, so how about 800 over 9? Something like that?
What's the square
And
root?
so then you take the, who cares? And so you take the square root and you get
think it
root
is.
800 over 9. It would work out to
Square.
10/3 times root 2 root 2. Root
Yeah.
8,
Yeah.
right? Because that's 8 times 100. The 100 comes out as a 10.
Yeah.
Then 8 is the same thing as 2 root 2.
Oh.
Yeah, but who cares? I don't care. That's not the point. The point, we could find it. We could find where it is, but it's it's not so easy, right? So, and I think I even did it wrong here. So, yeah, I did. Yeah, look at that. Another thing you could do, another way of doing it, is to just find whatever and then multiply by 10/3 at the end. You know, you could have just said, well, if we know that's -1, and we know that's 3, we could find this by saying 9 minus 1 is 8 squared and all that. Or, yeah, 8. And so then you take the square root, and so you get 2 root 2. Then you take it and stretch it out to 10. Like Victor said, you multiply by 10/3, and everybody gets multiplied by 10/3.
Yeah, that.
That, yeah, I like that better. I like that better. So, whatever, like however you want to do that, that's fine. There's one more thing we need to do. Everybody get that?
Yep.
Okay. So, yeah, so that's, and there's only one of those. There's only one of those, and I think it's an arctan. That makes your life a little bit easier, barely. But it's still, that's the idea behind it. So finally, let's do one of these. 12b. We are going to change coordinates from rectangular to polar. Now, here's the thing, and you say, well, wait a minute, but you told me that there's like infinitely many polar coordinates, like every, like they're not unique. Where r is positive and 0, theta is between 0 and 2 pi.
Okay.
Now it's unique. Everything's unique except for the point 0, but whatever, right? Like that's the weird, with 0, the origin is always weird. But here we go, okay? Now there is one unique way to write this, okay? And it's going to give us, so the point we're looking for is minus 4 root 3. Guess what the first thing I'm going to do is? Grab it. Okay? Rectangular, so there's a rectangular coordinate, so this is easy. Minus 4 up to 4 root 3. Yeah, that's terrible. So, wait a second. What triangle do we know that's kind of like this? What are the sides? 1,
2, or 3.
Okay. Does that look right? Yeah, the height here is, oh, that's root 3. And the ratio is root 3 to 1, right? So, yeah. So what do I need to multiply this guy by to turn him into that guy? 4. If I multiply everybody through by 4, so it's 8. Get 8. And so, okay, now, what's this angle right here?
Pi over 3.
Pi over 3. So that's pi over 3. So then if we want, that's not the angle we want. We want this one right here. So what is that?
Pi minus.
Okay.
Which is
2 pi over 3.
How about
Yeah.
that?
Pi over 3. Yeah.
Okay. So final answer is going to be r theta. What's my r?
8.
8. And what's my theta?
2 pi over 3.
2 pi over 3. There we go. All right. So this is, and this stuff's easy. Like you have 6 homework problems, real easy stuff. It's the, and I'm telling you, if you could do it like this, like I've been telling you since day 1, day 2, like if you have this stuff locked in your head, then you don't need to sit there and go, well, pi minus pi over 3. You just know that that's 2 pi over 3 because you've memorized the thing. You know where your pi's over 3's are, and you know where your all that. But anyway. But yes, you're absolutely right. I'm just picking on you, like pi minus pi over 3 is exactly what you're looking for. And so, okay, have fun, guys.